It's amazing, isn't it? Time just keeps ticking away, relentlessly, and we need to measure it with incredible accuracy. I mean, think about it. Your phone's GPS, cutting-edge research, all of it hinges on super precise clocks.
Yeah, exactly. And for a long time, the gold standard, like the top of the line, has been atomic clocks. They work by basically tracking those really predictable movements of electrons in atoms.
Right, those tiny little particles zipping around. But here's the thing. What if we could take it even further? Like, atomic clocks are fantastic, but what if we had a way to measure time that's even more stable, even less likely to be thrown off by, the tiniest little vibrations or changes in the environment?
That's a question that's really got scientists buzzing right now, pushing those boundaries, trying to find the absolute limit of how precisely we can chop up time. And that's what our deep dive today is all about, a whole new frontier in timekeeping, one that doesn't just look at electrons, but goes right to the heart of the matter, the nucleus of an atom, and specifically an atom called Thorium-229.
Thorium-229. Sounds kind of exotic. So researchers at JILA, working with the Technical University of Vienna, they're the ones at the forefront of this, right?
Exactly. They're really pushing the boundaries with what they're calling nuclear clocks. And what we're going to do is unpack all of that, why this could be a total game changer, not just for timekeeping, but for physics itself.
This is exciting stuff. Okay, so let's break it down. You mentioned atomic clocks and now these nuclear clocks. What's the core difference? What makes this new Thorium-229 approach so special?
Well, it really comes down to which part of the atom you're focusing on. With atomic clocks, you're looking at the transitions of electrons, how they jump between different energy levels in that sort of outer cloud around the atom's nucleus. And yeah, those transitions, they're very consistent, very predictable, but they can still be affected, even if it's just a little bit, by things like electric fields, magnetic fields, even tiny changes in temperature. All those things can introduce a bit of error.
Okay, so the nucleus, that's like the super dense center of the atom, right? Mm-hmm. Is it basically like it's more shielded, less affected by all that outside stuff?
Exactly. Think of it this way. The nucleus is bound together by what's called the strong nuclear force. And the energy transitions that happen within the nucleus, those usually involve way, way higher energies than the electron transitions we use in atomic clocks. But Thorium-229, this is where things get really interesting. It has this one particular nuclear transition that's surprisingly low energy. So low, in fact, that we can actually access it with laser light.
Wow, that's incredible. And this is different from the typical high-energy stuff you normally associate with nuclear reactions.
Exactly. We're talking about gamma rays and all that. But this Thorium-229 transition, it's something special. It's low energy. But because it's happening within the nucleus, deep inside the atom, it's much less susceptible to those external disturbances that can mess with atomic clocks. And this inherent isolation, this stability, that's what makes it so incredibly promising for building a new kind of clock, a clock that's potentially more accurate than anything we've ever seen before.
So it's not just a theory anymore. This isn't just some hypothetical idea on paper. These researchers, they've actually demonstrated this, haven't they?
Absolutely. And this is where that Nature publication from last year comes in. It was a huge e-moment for the field. Junya's lab at JLA, they managed to make the first ever frequency-based quantum state resolved measurement of this Thorium-229 nuclear transition. And they did it inside a specially designed crystal.
Okay, hold on. Break that down for me a bit. What exactly does that mean? What did they prove was actually possible?
It basically confirmed that this super precise, low-energy nuclear transition in Thorium-229, it wasn't just something we thought should be possible. It was something we could actually see and measure with the kind of accuracy needed for a clock. It went from a theoretical possibility to a tangible experimental reality.
Wow. So they've proven it's measurable. That's a huge first step. But I'm guessing there's still a lot of hurdles to overcome before we can actually have working nuclear clock on our hands.
Oh, definitely. It's still early days. And one of the biggest challenges is something that comes up in a lot of precision measurements: temperature. Even tiny fluctuations in temperature, fractions of a degree, can affect the materials, the environment, and ultimately the atoms or nuclei that you're trying to observe. So figuring out how to minimize those temperature effects is absolutely crucial if you want to build a truly stable, reliable clock.
Right, because even the tiniest change could throw off the entire measurement.
So that brings us to this latest research, the paper in Physical Review Letters, which focuses on exactly that: temperature sensitivity. Exactly. That's the paper you highlighted, right? And it really gets into the nitty-gritty of this challenge, how temperature can affect these nuclear transitions and what we can do about it.
And the lead author on this new study is Dr. Jacob Higgins. What did he have to say about the significance of understanding this temperature sensitivity?
Well, Dr. Higgins said this research was kind of like the first step towards really understanding how external factors might affect a potential nuclear clock, temperature being one of the big ones, of course. And what's really exciting is that they found a specific nuclear transition in thorium-229 that seems to be relatively insensitive to temperature. And that's exactly what you need for a high-precision clock, something that's not going to drift all over the place if the temperature changes just a tiny bit.
Relatively insensitive. That's good, right? Okay, so how did they actually test this? How did they figure out how much this thorium transition was affected by changes in temperature?
Well, they used a really clever approach. They embedded those thorium-229 atoms into a solid crystal, calcium fluoride or carrier-urus. It's a very specific type of crystal that allows you to pack a lot of thorium atoms together.
Okay, so they're not just floating around individually. Why use a crystal like that? What's the benefit?
It's all about getting a strong signal. You see, with ion traps, where you're suspending individual atoms in a vacuum, you can only have so many atoms in a given space. But with this solid-state approach, this crystal, you can pack in a much higher density of thorium nuclei. More nuclei means a stronger overall signal when you're trying to measure that very faint nuclear transition, which ultimately leads to better stability and potentially higher accuracy for your clock.
I see. So more thorium packed in means a clearer signal, a more precise measurement. Okay, so they've got this crystal with all the thorium embedded in it. What's the experiment? How did they test the temperature sensitivity?
What they did is basically put the crystal through a controlled temperature swing. They heated it up, they cooled it down, and they very carefully measured how that affected the energy levels within the thorium nuclei. They went to 3 specific temperatures. A very cold one, 150 Kelvin, which is about -123 Celsius. Then a middle temperature, 229 Kelvin, about -44 Celsius. And finally, they brought it up to room temperature, 293 Kelvin.
Okay, so they're swinging the temperature around, but how do they actually measure what's happening inside the thorium nucleus as the temperature changes?
That's where they brought in the big guns. They used something called a frequency comb laser. Think of it like a super precise ruler, but for light. It lets you measure the frequencies of light with incredible accuracy, and that's what they needed to do. Look for any tiny, tiny shifts in the frequency of the thorium-229 nuclear transition as they change the temperature.
Okay, so they're looking for these subtle frequency shifts. Did they find anything? Was it a straightforward result, or was it more complicated than that?
It actually turned out to be a bit more complicated than just a simple shift. As they changed the temperature, they observed 2 competing physical effects happening inside the crystal.
Competing effects? That sounds intriguing. What were they?
All right, so the first effect was pretty intuitive. As you heat up the crystal, it expands a little bit, right? And as you cool it down, it contracts. That's basic thermal expansion. But here's the thing. That expansion and contraction, it changes the spacing between the atoms in the crystal lattice, even if it's just a tiny, tiny amount. And those changes in spacing, they actually alter the electric field gradients experienced by the thorium nuclei embedded in the crystal.
Okay, so the crystal structure itself is having an effect on the thorium atoms. What was the second effect?
The second effect was also related to the expansion of the crystal. As those atoms in the crystal lattice moved slightly further apart or closer together, it affected the electrons. Specifically, it changed their density and how they were distributed within the crystal. And because electrons have a negative charge, those changes in electron density also affected how they interacted with the positively charged thorium nuclei.
So you have these 2 effects, changes in the crystal structure and changes in electron density. And they both have an impact on the thorium nuclei.
Exactly. And here's where it gets really fascinating. They found that for one particular transition within the thorium nucleus, these 2 competing effects, the crystal structure changes and the electron density changes, they basically canceled each other out.
Really? So the thorium transition, it stayed stable even though the temperature was changing?
Well, not perfectly stable. There was still a tiny, tiny shift. But it was incredibly small, much, much smaller than they were expecting based on previous studies.
Wow, that's amazing. How much smaller? Can you quantify that for us?
Across the entire temperature range they tested, from that super cold 150 Kelvin up to room temperature, this specific thorium transition shifted by only 62 kilohertz. To give you a sense of scale, that's at least 30 times smaller than the shifts they observed in other transitions. It was practically a flat line on their graphs.
That's a huge difference. No wonder one of the researchers, Chuang and Zhang, called this a game changer for clock applications. That level of stability is mind-blowing.
Absolutely. It's a really significant step towards building a nuclear clock that's not going to be thrown off by even the tiniest temperature fluctuations. But even with these incredibly promising results, the researchers are still pushing further.
They're not satisfied yet. What's next? Even more stability.
Precisely. They think there might be a sweet spot somewhere between those temperatures they tested, 150 Kelvin and 229 Kelvin, where the nuclear transition is even less sensitive to temperature changes. Their ultimate goal, the target they're aiming for, is a fractional frequency stability of 10 to the power of a -18 for continuous operation in a compact nuclear clock.
10 to the power of -18. I can't even fathom how precise that is. And they think they can actually achieve that.
That's the dream. To give you an idea of how ridiculously stable that is, a clock with that kind of accuracy would lose less than 1 second over the entire age of the universe. It's almost unbelievable. But that's the level of precision they're striving for.
It's amazing how they can even measure time with that level of accuracy. What kind of equipment do they need to do this? Is this stuff off the shelf or custom built?
Well, when you're pushing the boundaries of science like this, you often need specialized tools. Dr. Higgins and Tian Oi, another researcher on the team, they both talked about how important JILA's instrument shop has been for this research. They have incredibly skilled machinists and engineers there who can build custom parts for their experiments.
So things like the crystal mount or the temperature control system, those had to be custom made.
Absolutely, and that in-house expertise, it's invaluable. It means they can make tiny tweaks to their designs, try out new ideas, and make sure that every single component, no matter how small, meets the incredibly demanding requirements of their experiments. Dr. Higgins even said that without these custom-built parts, they wouldn't have the same level of confidence in their results. And Uy emphasized how much time it saves them, being able to design and build things in-house.
That's really cool. It's like this perfect blend of cutting-edge science and old-school hands-on craftsmanship. But okay, let's zoom out for a moment. We've talked about how stable these nuclear clocks could be, but the implications of this research go far beyond just keeping better time, right? There was something in the background material about using these clocks to study fundamental forces of nature.
That's right. This is where things get really exciting. You see, because that thorium nuclear transition is so incredibly insensitive to all the normal environmental stuff that messes with other clocks, it becomes incredibly sensitive to something else. Tiny variations in the fundamental forces of the universe.
Fundamental forces? You mean like gravity, electromagnetism, the strong and weak nuclear forces, the stuff that holds everything together?
Exactly. And maybe even other more subtle forces that we haven't even discovered yet. Any unexpected change, no matter how small, in the frequency of that thorium transition, it could be a sign of something new, something that goes beyond our current understanding of physics.
Wow, that's a big claim. What kind of new physics are we talking about here?
Well, one possibility that's getting a lot of attention is dark matter. It's this mysterious stuff that we know exists because of its gravitational effects, but we've never been able to directly detect it. Some theories suggest that dark matter might interact with normal matter through extremely weak forces that we haven't been able to measure yet. And here's the thing. A nuclear clock, especially one as sensitive as this Thorium-229 clock, it might just be sensitive enough to pick up those tiny, tiny dark matter interactions.
So they could potentially use a clock to detect dark matter. That's incredible. It's like turning timekeeping into a tool for exploring the fundamental mysteries of the universe.
Exactly. It's not just about keeping track of seconds and minutes anymore. It's about using those ultra-precise measurements to probe the deepest secrets of the cosmos. And while this research is definitely pushing the boundaries, it's important to remember that it's built on decades of work in atomic clock technology. It's a natural progression, a constant striving for greater precision, greater understanding.
Okay, let's sum things up for our listener. What are the big takeaways from this deep dive into nuclear clocks?
First, the big promise of Thorium-229 nuclear clocks. They have the potential to be incredibly stable, much more so than anything we have now, thanks to that special nuclear transition and how well it's shielded from environmental noise. Second, the recent breakthrough by JILA, where they demonstrated a specific thorium transition that's remarkably insensitive to temperature changes. That's a huge step towards making these clocks practical. And finally, the truly mind-blowing possibility of using these clocks to explore fundamental physics. Things like dark matter, new forces, things we can only dream about right now. It's a whole new way of looking at timekeeping, not just measuring it, but using it as a tool to unravel the deepest mysteries of the universe.
So for those of you who love to dive deep into complex topics, hopefully this has given you a good grasp of this revolutionary technology. It's not just about keeping better time. It's about potentially changing our understanding of the universe itself.
And it really makes you think, doesn't it? If we can define and measure something as fundamental as time with such incredible accuracy, what else might we be on the verge of understanding? How might these new ultra-sensitive tools change the way we see the world, the way we develop technology, the way we understand our place in the cosmos? It's truly an exciting time to be following these advancements.
It certainly is. And for those who want to explore further, you might want to look into the basics of atomic clocks. It's fascinating stuff. Or maybe delve into the mysteries of dark matter. There's so much out there to learn. Thanks for joining us for this deep dive.